So, welcome everybody to our 1W-MINDS talk of Lorenzo Rosasco, which is going to be about interpolation and learning with scale-dependent kernels. So, Lorenzo is currently professor at the University of Genova, and he's also at the same time a visiting professor at MIT, and he's involved at the Italian Technological Institute, so IIT. He coordinates the Machine Learning Center Malga in Genova, and if you ever get him to invite you, it's a very nice experience, the talks they do and how they do the visit. I speak from experience. And at the Laboratory of Computational and Statistical Learning, which is focused on the theory of algorithms and applications in machine learning. So if you want to know a little bit about his background, he did the PhD in Genova. He was visiting a lot around Europe and the United States. He was at MIT, in Chicago at Toyota Technological Institute, and he even visited Austria at the Johann Radon Institute. And then as a postdoc, he moved a little bit more around the world. So again, in MIT and other departments. And this is also where I met him. You wouldn't have recognized him now. He was shaved and he had a crew cut. So the pre-hippie phase. So currently he's a fellow in ALICE. So this is the European Organization for Theory that promotes machine learning. He's also co-director of the Theory, Algorithms and Computations of Modern Learning Systems program and the ALICE unit. And he is proud recipient of many, many grants, including the FIRB and an ERC Consolidator grant. So if you want a job, he's a good person to ask. So thanks for giving this talk. We're really looking forward to it.
Okay, thanks, Karin. Thanks for the invitation, the organization. And thanks for everybody to connecting. Yeah, so I'll jump right in. So this is a work, actually, it's been one of the longest work I've done, I guess partially because of COVID, but not only, it's been dragging for a while. There is one paper online, but it's not really updated. And so this is kind of a preview of something which is not really published yet. Is a collaboration with Ernesto De Vito, who's a professor in the math department here in Genova, and Alessandro Rudi, who's a researcher in area in Paris, but especially of Niccolo Pagliana, who's now graduating, and he actually spent the second half of his PhD working on this. The context of what we're doing is somewhat, something that has become very popular in machine learning in the last few years, which is this a host of empirical observations, largely related to deep neural networks, that seems somewhat to put into discussion the very foundations of learning theory from a statistical point of view. So there is a well-established statistical learning theory, which is roughly based on the idea that when you try to get a model that is predictive, and you only have at disposal finite amount of data, you should impose some kind of constraint and then trade off the constraints with fitting the data, okay? The general principle of regularization, okay? And so to illustrate this idea, oftentimes what is presented is the picture here on the left. Can you see my cursor moving? If I do this, okay. So where basically what you say is, if you look at the training error, if you make your model more complex, it will go down. But if you look at the test error, the test error can go up, okay? So you have this, if your model is too simple, you cannot be predictive. Your model is too complicated, you might not be predictive again, okay? And all of a sudden, there are plots like the one on the right, and I'm sorry, there is a flip, but this is because I just took this from the paper. So on the left, low is good, because that's error. On the right, high is good, because it's accuracy. Okay, you should flip it in your head. So what you see, the thing you should notice is that this thing goes up, but it doesn't go down. Okay, so it looks like if your model gets more complex, it doesn't hurt. Okay, there is a small detail. If you look at the x-axis, this is actually not the size of the model; it's the number of iteration in your training. This is there is now an established fact that as you go on and train more, your model becomes more complicated. Okay, but this is maybe something we've overlooked for now. So the main point here is this idea that your model, this trade-off doesn't seem to be there. And then the ansatz has become make your model large and complex. okay? And all of a sudden there is like, okay, you know, what about everything we know? Do we have to throw it all away? Do we need to reinvent the theory from scratch? Because again, the observation, the initial foundational results that we built our understanding on doesn't hold anymore, okay? This is somewhat the dramatic introduction of a whole host of recent research into try to develop new ideas in machine learning. I didn't say this, but it always works. I become proficient in reading chats and being interrupted while I speak. So if there is anything along the talk you want to know, just interrupt me. All right, so on a personal note, when I started to see this stuff, I was a little bit nervous and sad because being somebody that spent like 10 years at least of his life doing theory of machine learning, the idea that everything I did was totally useless and maybe wrong to explain whatever you see in practice was a bit unsettling. And so, of course, this caught my interest, and I got curious to see what was going on. And so what I'm going to tell you about is our effort to understand a bit this empirical observation and see to which extent we have a theory that explains them. And let me say that it started off as an understanding pursuit where we wanted to try to see what was going on and see a mathematical reason. And indeed, we were hoping to get very sharp mathematical results, okay? In the process, I think what we found out is more mathematical results in the sense of what you find sometimes in physics, in the sense that we didn't get the mathematical results as nice as we hoped for, but we still got mathematical results that I think do explain practical behavior, okay? You'll see what I mean in a minute, because you'll see that the results we have some very negative drawbacks, okay? But still they seem to be able to predict well what happens in practice. Okay, let me jump and tell you a bit what we did. So before, I just want to set up the stage with the setting I have in mind, and this is going to be the vanilla, super classic statistical learning theory, okay? So there should be no surprise here. So what's the idea? In words, you would like to make the future error small, but all you have is current data, okay? So you have to say what you mean by future error and current data. So what you say is that there is a probability distribution over a set of input and outputs, and your goal is to predict functions, okay? So the future error, you abstract by saying that, doing something that you cannot really do, of course, in practice, you define the error, here is just least squares, over all possible pairs of data, weighted with respect to the probability of being sampled. So this is just an abstraction of the test error, okay, of your future error. And you would like to make this small, but you don't have access to this because typically the distribution P is either unknown or hard to compute. And so what you have at disposal are a set of samples that you assume to be identical and independently distributed with respect to the distribution. Okay, so this is the learning problem because you only have data now, but you would like to learn something about the underlying distribution, okay, in terms of predictions. Okay, so the problem of this you will never be able to find an exact solution to this problem because it's like a problem where you only have noisy, imperfect data. You don't have access to the integral, but only to finite data. And the classical way to solve it is, too much. You have to do two things, okay? Maybe let me also point out one thing that I didn't say. Sorry, there is a delay in my. Okay, notice also that in principle, you would like to minimize and find the best solution, the best function over all possible functions in the universe, okay? Mathematically, this would be the set of measurable functions for which your integral is well defined. However, in practice, also this is a problem because you never have access to all the functions in the universe, okay? So you don't know the integral, you don't know the function in the universe, what do you do? The classic approach, if I manage to turn my slide, seems to be more complicated than expected. You replace the integral with the sum over the training data. You replace with the space of all the function in the universe with the space you can handle. Hopefully very large. You would like this space H to be as large as possible. This is what sometimes is called the hypothesis space. And so you replace this ideal problem integral all function in the universe with this practical problem, finite sum on the data and a large space that you can somewhat handle both statistically and computationally. This is the basic idea in empirical risk minimization. Man. Okay, so sorry, I'm afraid this is going to happen. For some reason, there is a delay. So we look at a particular example of this, okay, which is exactly the empirical risk minimization, but it has to exist that we take the hypothesis space to be what is called the reproducing kernel Hilbert space, okay? This the introduction of this kind of spaces is not particularly short. They have a lot of properties, okay? But for what you care up to now, you can think of these as extremely large spaces, okay? They are Hilbert spaces. And the norm in the space typically can be seen as some form of regularity, describe some form of regularity of your function of interest, okay? So H is, for example, the space of all function with a polynomial decay in Fourier, let's say. And the norm is some kind of constraint on the speed of decay in Fourier. This is the classical example which corresponds to considering Sobolev spaces. In such a large space, you might want not only to minimize over the space, but to possibly consider adding a penalty, okay? Where basically you say the space is so large that I want to have a way to look inside the space, okay? And by choosing lambda appropriately, for lambda large, you look at functions that are very regular. For function, when lambda gets smaller, you allow yourself to functions that are less regular, okay? This typical situation is where you let these lambda be bigger than 0. In this talk, I'll be interested in the situation where lambda can also be 0, okay? Okay, so one obvious question is, well, the second ago, I didn't have the penalty. Now you have the penalty. Let's talk about it. Why are you doing this? What's the reason for this? Do you want to do it? Do you not want to do it? This is going to be the discussion. Before doing that, let me tell you one more thing about this problem, okay? If you look at the solution of this problem, okay, there are a bunch of reasons why you want to do it, but if you look at the solution of this problem, you have the nice fact that is given by this reproducing kernel space that you can write the solution in explicit form. Okay, and it looks like this. This is a standard fact known as the representer theorem. The solution to this problem is a linear combination of this kernel function at the training set points with coefficients given by the solution of this linear system. K hat is the matrix with entries given by the evaluation of the kernels at the training set points. Y hat is the output, is the vector with all the outputs stacked on top of each other. Okay. From this perspective, if you're familiar with inverse problems or the solution of linear system, you can view this as some form of regularized, or if you want, better conditioned solution of a linear system, okay? Whereby increasing the value of lambda, you make the problem more stable, the solution of this linear system more stable because it becomes better conditioned, okay? So if you want, one way to see the effect of lambda is the one of basically saying, well, I'm doing an inversion, and I want this inversion to be stable. And so, because otherwise, both numerically and statistically, I may have a crazy behavior. And so the idea is, let me add lambda. Okay. Far so good? Opa. All right. So in the next few slides, I'm going to give you some discussion and motivation of why you might want lambda, and perhaps some guesses of why you might not want lambda. Okay, so at the beginning, we'll take the more classical point of view, which never put too much into discussion the fact that you need lambda. Okay, and here is one possible reason why. If you look at this matrix K hat and you look at its action, you can write it down like this. And you can view this expression as an approximation of the action of an integral operator. Okay, which is just the what's it called? The integral operator with kernel K, okay, which is easy to see and is a standard fact that under mild assumption is a compact operator. It has a lot of properties, but it's a symmetric compact operator, self-adjoint and compact operator, which means that when you try to invert this operator, okay, in general, you'll get an unbounded operator. So if you just try to invert this, the inverse is unbounded, okay? So if you view this as an approximation of this, and in some sense you think, okay, the object I'm trying to approximate is not invertible. When I use this and as an approximation, I try to invert it. In general, I will expect that for n going large, when I start to have enough data, also this will not be invertible, and the condition number can be very bad. And so maybe I want to try to add a regularization. Okay, so it's like a sequence of finite rank operators converging to a compact operator that is not invertible. And so the idea is, if this approximation here is good, okay, maybe you need a regularization because this is not invertible, and hence you might expect these to be not invertible. Okay. I think for many, many people, certainly for me, this was one of the main accepted intuitions to justify why you might want to add lambda. As you'll see in a minute, and maybe if you don't agree with this intuition, you'll be happy in a minute. In fact, one can question this intuition. Okay. Before we do that, notice we want to go back to one detail of what was discussed before. I show you again some of the plots, empirical plots that came out in the last few years. These are papered by several colleagues. Particularly, look at the one on the left. It's the same plot, okay? There is the error here, and then here, this one is lambda, okay? And here is just two kinds of kernels. One is the exponential kernel, or let's say one is the Gaussian kernel, and one is the exponential, which is the Gaussian without the square, okay? What is sometimes called the Abel or Laplace kernel. And again, what you see is the same story I told you before, even more clearly. Here, what you see here is actually 1 over lambda. When lambda goes to 0, I don't see any overfitting. I don't see any instability. I don't see any big variance, okay? It's just the test error is just good. The same thing I showed you at the beginning, more specifically for this ridge regression, regularized least squares algorithm, okay? So and so again, this seems to contradict what I just told you, the intuition that when lambda goes to 0, okay, I'm inverting a matrix, it can be unstable, and I might observe unstable behavior. Here, there is no instability at all. When I look at this stuff, my question was always, okay, but these kernels do have some parameters inside. How do you pick this parameter? For example, if you look at the Gaussian, is this a narrow Gaussian or it's a very large Gaussian? Okay, because this should change the shape of this curve. The reason why I asked this question is because my master thesis was about choosing lambda and the kernel parameters for, at the time, SVMs. Okay, and so I basically grew up looking at picture like this. Picture like this, where you put instead of just looking, it's the same as this one. Here, only here there is lambda, and here is the test error. Here, there is still lambda, but here there is also the kernel parameter. So look at either this kernel or this one, you see that there is a kernel parameter, the width of the Gaussian. And so what you see is that you get the curve, you get different curves depending on how you pick gamma and lambda. You can look at different level sets, right? And so, for example, if you look at certain gamma, you might get this behavior, okay? And if you look at some other gamma, you get this behavior. So I knew this since I didn't have a beard and I was not in my hippie phase. So the question for me was always, okay, what are you showing me? Could it be that you're just showing me the wrong picture, and you're showing me this picture, but actually you could also show me this picture? And so this pointed me at basically asking the question of, okay, if we want to study this particular example where we do kernel ridge regression with kernels like these guys that depends on the scale, let's figure out the role of the scale. Notice that the scale, as I'm going to describe in a minute, has various meaning, but can be related to the idea that this space can be large or small, okay? Indeed, this is the classical intuition, I would say. If you take exponential or Gaussian that are very narrow, you allow your function space to contain function that can have a very oscillatory behavior, okay? Because your Gaussian are narrow and you can actually resolve very oscillatory behavior. If you take freaking huge Gaussians, okay, when you combine them, you get something extremely smooth. So in the context of deep neural network, we talk about overparameterization. In this case, the term doesn't quite apply, but gamma small, okay, correspond to large spaces. So if you want this overparameterized. The term really doesn't make any sense, but what I mean is that the space is more complicated. When you take gamma much smaller, much bigger, okay, then the space is effectively contains simpler function. So while this is not overparameterization, it goes a bit in the direction of getting something large and something small, okay? And the classical intuition is if you take gamma too small, you might overfit and get an unstable behavior because your function become more complicated and you might get this unstable behavior, okay? And so my master thesis explanation for this plot was you have lambda, you have gamma. When lambda is small, you overfit. When lambda is big, you stabilize. You have gamma, gamma is the size. When gamma is small, you overfit. When gamma is large, you might oversmooth. And of course, there is the in-between. Okay. All right. So this was master thesis me, and hopefully everything I said relate probably not to the youngsters, if there is anybody, but if you learn a bit about machine learning, you know, from the classical point of view of bias variance trade-off, this is the stuff, the empirical observation you should have seen before. Okay, the next few slides are basically questioning this point of view. Okay, so I'm gonna, you know, the story is before you have to wait a bit more for the math. The story goes on a little bit more. So the story starts by a fact that I know since forever, but I somewhat always crept under the rug, which is that if you take a Gaussian kernel or an exponential kernel, these are translation invariant kernels. And if you take a bunch of distinct points, the kernel matrix is going to be always invertible. Okay, so the idea that the kernel matrix is very ill-conditioned could be the case, but the matrix is strictly speaking invertible. Okay, not only that, if you now let lambda go to 0, what you get is not just any solution, is the so-called minimal norm solution. So if you just take the same expression I did before and you get lambda go to 0, the matrix K is going to be invertible, and what you get is a solution that perfectly interpolated the data, but among all the solutions that interpolate the data is the one with the minimal norm. Okay. All right. So maybe, you know, at this point, my thought was like, so I could expect interpolation. I don't expect a crazy interpolant. And I know that this guy is invertible. So let's look at its condition number, because after all, my intuition about why I need lambda is because the condition number can be bad. Okay. And so I start to ask myself, what is the behavior of this condition number over, let's say, the smallest eigenvalue of this matrix? Okay. And I start to ask myself how gamma, the scale parameter, affects the smallest condition number, because this might explain what happens in regularization. Okay. So it's easy to convince yourself that the smallest eigenvalue of the matrix of a translation invariant kernel is going to at least depend at least on two things. The first one is the one here on the right, okay? Is the minimal distance between the point. Because basically what you're doing is you take a bunch of points, you take the distance of everybody against everybody, and then you shove it on top of an exponential, okay? If the points are far away, the matrix is going to have a large rank. If the matrix, if the points are to be close, imagine the limit case where 2 points coincide, then the rank is going to be deficient. When the points start to be very close, even if they don't coincide, the eigenvalue are going to be small. Okay. So if points are close, I'm going to expect, you know, the matrix to be ill-conditioned. If points are far away, where far away and close must be quantified, then I can expect the matrix not only to be invertible, but to actually be very well conditioned. If you do a back of the envelope computation, what you imagine is that pick points in high dimension, okay? Say, when I say high, I mean 5, okay? If you take points uniformly in 5 dimensions, the probability they become close is very low, okay? You basically need a number of points or than 2 to the 5 before you actually see points getting close with a high probability. And this probability, if you are in 10 dimensions, become exceedingly small. Okay, so if you're on a regime where n is smaller than 2 to the d, which often happens in practice, then you expect this matrix to be not only invertible, but the smallest eigenvalue to be reasonably large. Okay. Moreover, if you look at the shape, I told you, you take the distances and you shove it on top of an exponential. You do more because you actually divide by the scale. And so by choosing the scale to be small, you're effectively zooming out, the points. It's as if you were pulling the point more far away. So if you take sigma to be small, the points are more far away and the smallest eigenvalue becomes larger. Okay? So this suggests, and the other way around, if you take gamma to be large. Of course, there is a limit case where you take gamma so small that all the points become orthogonal and you get the identity, okay? But before that, you have this phase where the condition number becomes good because you just are pulling the points apart. So this is the first indication that if you look at the behavior of the smallest eigenvalue of the matrix with respect to gamma, you expect the matrix to be better conditioned, okay? So potentially lead to more stable behavior if you take gamma, the scale of your bells, to be small, okay? All right, so this is the first clue of what may be going on. Now I'm going to give you the same exact intuition, but instead of in space, we're going to look at things in frequencies, okay? And here is the reasoning. If you look at the smallest eigenvalue of the kernel matrix, the kernel matrix is going to be a rank n operator. It will not be able to approximate all the eigenvalue of the true integral operator, but at best is going to be able to approximate the nth one, okay? So now we can do the following. Analytically, being mathematicians, we can, you being mathematicians, you can plot the eigenvalue decay of this operator, okay? And you can plot this for different gamma, and then you can look at the nth one. Now, LK, if you choose the Gaussian kernel, the exponential kernel is going to be a convolution operator, okay? And by associative principle like ideas, if you make the operator, if you make the kernel very localized in space, then you're going to have a much lower decay in frequencies, okay? And the other way around. In other words, pick, say n is 200, look here. If you take gamma to be large, okay, then you are you're more unlocalized in space, and so you have a faster decay in frequency. If you take something which is more localized, your frequency decay becomes lower, okay? If you now look at this eigenvalue, you see that it is the same observation as before. When gamma is smaller, the eigenvalue becomes larger, okay? That's this effect. Again, green curve is wide Gaussians, okay? Fast decay in Fourier. Blue curve is narrow Gaussian, much slower decay in Fourier. So by making the space larger, you're making the matrix better conditioned, which to me was not a familiar intuition. This was a new observation to me, okay? And as I'm going to show you in a minute, this was the very basis of the mathematical results coming up in a second, okay? The idea to me knew that this suggested that by making the space larger, you can achieve improved stability if you look at the condition number of the matrices that define your algorithm, okay? So the idea is that now we have these two intuitions. On the one hand, we have this idea that if you make your Gaussian smaller or your exponential smaller, you have a more complicated behavior. On the other hand, with this other intuition, which is a bit newer, let's say, that by making your Gaussian smaller, you can make them better conditioned. And we want to resolve this and see how much of the old theory can explain this and how much we have to update it. Okay? All right, so this was the blah blah, okay? This was the story, okay? And this is really how it started. I started to think about this stuff with my colleagues, and we start to try to build a physical intuition, and then we try to sit down and do the math to see if this was there was something true in what I just said, or is just wrong. And to resolve this apparently contrast with these two intuitions, one which was classical and one that, at least for me, was a bit newer. This idea that larger space can give better condition number. So what did we do? Nothing. We killed lambda. We just killed it. So when you see this f at gamma, this is the minimal norm interpolation with the kernel of scale gamma. Okay. And what did we do? We did the classical statistical analysis. What you see here is what is called the excess risk. Is the and in words, the interpretation is the difference between the prediction error of your solution and the best possible prediction error. So both this quantity you cannot really compute in practice, but you can study mathematically. Okay. So more or less when we started this project, after a few weeks, we got what I would call the cold shower. Okay. Because what we got is there was a paper by Sasha Raklin and a student that showed that this algorithm, the minimal norm interpolation, if you use kernel like this one, which is basically an exponential kernel with some normalization, there exists no choice of gamma that allows this method to be consistent. Okay, so of course you would like the error to go to the best error, but there is a result that says that this is not possible. Okay, you cannot hope this method to have the very basic property of consistency. So this is at the same time unsettling, because all of a sudden, most statistics work in the regime where you have a lot of points, you're close to consistency, and you look at minimax rates. Okay, and this is your crouch in saying that your algorithm is good or not, because you have an upper bound, and then you will have a lower bound, and you can say, oh, see, sure, maybe it's asymptotic a bit, but everything works because the upper bound and the lower bound match. But here we don't have that anymore, because all of a sudden, we know that we will not converge. Okay. On the other hand, we kind of expected this anyway, because we know that if you start to be in the regime when n is exponential, and eventually you get to that regime, points are going to be close. Kernel matrix will now become invertible, and good luck try to stabilize a compact operator by doing nothing. Okay, so it's not so surprising that this doesn't work. And so with the fear of walking in unsettled territory where you have no convergence, we try to develop bounds that will still following the intuition and see how well, if they were useful to something. So what did we do? Okay, here comes the math. We just take the simplest model and we said, okay, let's not worry about approximation too much. Let's just say that we take a function which is in this space that we chose, okay? And let's assume that this function is available only up to some noise and up to the sampling of the input points. So it's just a particular case of the model I show you in the very second slide, okay? Remember, f star is going to be the best, okay? Is the true function. And then what did we do? First of all, let me rewrite the minimal norm solution, okay? This is just a rewriting. This is the minimal norm solution at a point that can be written as this was the coefficient C, okay? And this is just another way to write down the linear combination, okay? This kx x hat is just the vector with this form. So if you remember vaguely, there was a linear combination of kernels with some coefficients. This is the same writing, exactly, okay? Just a slightly more compact form without the sum. So we want to compare this guy to the best possible function. What do? We introduce an intermediate guy. The only difference between this is that you see I put a star here because I don't have access. This is an idealized object, which is the version of the minimal norm where I have access to the true value of the function. So here I only have access to noisy values. Here I actually have access to the true values. Okay, no noise. So this is exactly the minimal norm interpolation with no noise. So I give you a function value at 10 points and I ask you, give me the minimal norm interpolation that is now a globally defined function with minimal norm that passed through these points. Okay. So the idea is that we want to compare this guy and this, and then this guy and the true function. Thank you. Okay, this is it. So notice that I dropped the dependence on the kernel for now because it just overloaded the notation, but you can think that there is a gamma everywhere. I just dropped it to lighten the notation a little bit, okay? So here I have f at gamma minus, if you want, f at gamma star, then f at gamma star minus f star, okay? So the first term is the difference between these two. Is the same stuff, and I just have y hat, f hat. And so what is this? It's just the difference between the two. It's just a noise. Okay. What is this? This is just the difference between the true function as it is interpolation based on n evaluations at the input points. There is no noise here. Now, these two terms, depending who you are, you might want to give different name. From a classical statistical terms, the first term looks like a variance, and the second term looks a little bit like a bias. Okay. The truth is that the first term depends on the noise. The second term is not only a bias, it also depends on the sampling. So you can also call it an interpolation error or a sampling error. Is the difference between having the true function and having a global interpolant with minimal norm. Okay. So what we want to ask is, what is the behavior of these two? Spoiler, these two are going to have very different behavior in gamma. This one is going to like small gamma because it has the smallest eigenvalue inside. This one is going to like large gamma because it's trying to do interpolation with no noise. Okay. All right. So I don't think we. So let me skip a bit the shape of the. Let's see. This part is. I'm going to give you a couple of details, but they're not super important for what comes afterwards. Okay. So the first point is the interpolation error is related to how well the sampled point approximates the true operator. Okay. So if you look at, remember, LK was the true operator. P hat is just a projection on the subspace, induced by your training set points. And if you look at this error, it's going to be something that has a PCA or best finite rank like look. Okay. And so it's going to depend, if you wish, on how well this the subspace defined by this, or let's say this projection, describe this finite rank operator. So that's one thing we will have to study. Okay. The other thing we need to study is the variance part. The variance part looks like this, and let me explain a bit the pieces that comes inside. First of all, you see that there is the noise. You expect this because remember, this was essentially the inverse of the kernel matrix times the noise. So here is the noise, okay? Here is the inverse of the kernel matrix. But then what we do is that we exploit, remember, this is not just, this is learning. So there was this extra term in front, okay? And what we care about is not the function themselves, but is their prediction. And so exploiting this, we get something better. We don't just get the smallest eigenvalue, but just get this quantity. In some sense, this is some notion of condition number. The numerator is empirical. The numerator is what is called the effective dimension, which is this quantity here. For those of you that, are a bit familiar with the analysis of nonparametric learning, this is a very common quantity. How do you interpret it? Is the sum of all the eigenvalues of the true operator up to scale tau. It's basically counting how many eigenvalues you have up to some scale. Okay. And what you hope is that by having this is a bit, if you have nothing, you pay this, okay? But what you hope is that somewhat this term can counterbalance the effect of this conditioning a little bit, okay? This is because, again, we put here the error in terms of prediction, okay? So we get some saving grace here. So you put it all together and you realize you have these two terms, okay? This result holds for any kernel. There is no specific assumption on the kernel. This could be exponential or not, okay? As long as the smallest eigenvalue is bigger than 0, you can write down this bound. Of course, if this happens to be 0, this doesn't work at all, okay? So how the story proceeds is basically that we have to, and let me also say, from a technical point of view, this is quite easy, okay? This is more or less putting together simple basic facts about ridge regression. What comes next instead is a bit more annoying, because what I have to do is that I have to say, okay, now I want to look at translation invariant kernels. Specifically, I'm going to look at Sobolev kernels, and I want to basically turn all this quantity in explicit quantity that are going to depend on the number of points, the dimension, okay, some properties of the distribution, such as the norm of a star, perhaps, and then the scale. I want the scale to appear because I want to see how these two terms behave with respect to the scale. Okay. Usual story. I do this, then I go back. So the class of kernels we consider, okay, are at the same time super simple and super ugly. They're super ugly because this is the expression. They're super simple because they are just the kernel that correspond to Sobolev spaces. Okay, so you see there is a parameter nu here, and the parameter nu governs how many derivatives you have. Okay, so nu, to have reproducing kernel-based space, you have the Sobolev embedding theorem to hold. So you need nu to be larger than d divided by 2. Okay, and then the largest is nu, the smoother is the space. This is ugly, but if you look at the first three examples, they look much more familiar. If you look to nu equal 1/2, that for us is the smallest, okay, is the largest space we can consider. This is just the exponential, the one I've been talking about throughout the talk, okay, not the Gaussian. The Gaussian will have an exponential decay in Fourier. This one has a polynomial decay in Fourier. If you took nu equal 3/2, so you start to make the space smaller, the kernel corresponds to basically the multiplication of this exponential by some polynomial stuff. If you take nu equal to 1/5, there is more polynomial stuff. By increasing this power, you make this smoother and smoother and smoother. Okay. So these kernels are going, and you see that gamma appears both here and here, but you also have this extra parameter nu, which is also going to play the role of making your space larger or smaller. Once you have this, basically you have to take the quantity I showed you before, you mix a bit, you have to prepare a cake where you put a bit of interpolation theory and a bit of probabilistic theory by computing distances. And then you got this beautiful bound, okay? In its full glory. The bound is arguably incomprehensible, but let me point you what you have to look at, okay? Remember that we have, we start our journey with a guess of what we should see, okay? So let's see what we see here. This is interpolation. This is sampling. There is no noise, okay? We expect that as the number of points goes to infinity, this should get better and better because I have a real function. I only have an evaluation. I want to interpolate it. I give you more points and more points. This should get better, okay? And it does. Up to a log terms, it decays as n to some power. Then there is gamma. What I expect, if I start to put gamma too small, I'm just putting a delta on each of the points. Good luck, try to find a good interpolant of my function, okay? Whereas if I make gamma larger, okay, this area is going to become better. There is a power, and so this is what we expected. This guy doesn't like small gamma, he does like large gamma. If you look at the power, what you see that the effect is amplified by nu. So when nu is small, this term sucks. When nu is large, this term gets even better. Let's look at the variance. The exact shape of this is not so important for now. Let's look at the variance. What did we expect? Well, we hoped it would get better when gamma was small, because we said gamma should cure the ill conditioning, and it does, okay? It does, and nu further help. So when nu is small, it's even better. What we see here, and again, we expected this given the results by Sasha, if n is large, this term explodes. The points start to be close. You start to be in the regime where they occupy the space. The smallest eigenvalue gets close to its population version with infinite data, and they explode, okay? Of course, the fact that this explodes and this does not still leaves hope, because you can try to balance the two terms, but it turns out that even if you try to balance by choosing the best gamma, the overall error diverges, which again is what you expect from the lower bound. The lower bound was just for one kernel, but can be generalized for all these other kernels. All right, so this is pretty much the end of the mathematical part, right? And you see, it's a, I would call it bittersweet, okay? It's sweet because we started from an intuition, we tried to develop the mathematical theory, the equations do say what we wanted to say, okay? It's a little bit bitter because we found a bound that is diverging, and some of the constants here are exponential in the dimension, because the proof technique used Fourier analysis argument that we are going to give you some volumes essentially, and so you get constant or exponential. So what I want to tell you next is, one, how does this compare to what was done before in the theory, okay, of trying to explain this? We are not the first to have results for this. Let me tell you what other people did. And let me just show you then some experiments to argue that these bounds are actually not so bad. You know, they're actually useful for something. Let me do my usual game. Okay. So among all the stuff that I wrote that are a distraction, perhaps the main important point is this comparison with other people. So maybe let me go back so that you have distractions. There is a series of work that consider asymptotic matrix theory point of view, where you let the number of points and the number of dimensions go to infinity. The problem with that I don't understand and it makes me trouble is that by changing, if I fix the dimension and I move the number of points, the problem stays the same. There is f star. I can talk about f star. There is only one, okay? If I let n go to infinity, but also decon to infinity, I'm actually changing the problem at every step. And I have problem wrapping my mind around that model, okay? It's very popular. I like it. We also try to have some results on that. But I think the situation where you fix d, you fix n, and then you move n, is closer to reality, okay? So we wanted to try to keep that situation. And we wanted to work in the situation where n is smaller than 2 to the d. So d doesn't go to infinity, okay? There are very few papers that do this, that fix the dimension and doesn't let it grow. The main one is this one paper by, there are a paper by Sasha Racklin and one by Peter Bartlett. Okay, the paper by Peter Bartlett is very comparable to what we do. They actually get better results because they do get consistency, but their model does not correspond to a real kernel that you can implement. So in some sense, they said something like, if I could find a kernel such that its spectrum has this property, then it would be consistent. And they prove it, okay? But there is no such kernels for now, okay? So to some extent, our results are not as nice because they do, but they do work with the object that do exist and we can build. The results is nicer and leave open the question of whether we can find that kernel, okay? That this kernel that will the whole thing be consistent. All right, that's basically it in terms of you know, main coordinates of comparison. Let me show you a bit some of the empirical results. Okay, what did we do? We took just a situation where we knew everything and we tried to plot the bounds against the simulated version of the error. So say the test error, I can simulate. Let me see how it behaves. The interpolation error, I can simulate. Let me see how it behaves. And let's plot it against the bounds, okay? So the basic setting was this one. We did some Gaussian noise and some smooth function, which was arctan, okay? And every time we did a bunch of trials to have mean and average of our experiments. Look just at the plot on the left. The plot on the left, you should read like this. The blue points are simulated data that should mimic the true behavior, okay? The true behavior of what? Of the interpolation error. The green line is the linear fit. This is a log scale. This is the behavior of the bound, or let's say of the interpolation error with respect to the number of points, okay? What is the, or so the blue and the green is the truth, so to say. The orange is what is our bound up to the fact that we know that the constants are bad, so we try to fit the best constant. So we believe the power law, we don't believe the constant, so we fit the best constant. And again, you see that it's not super duper perfect, but I would say it's pretty good, okay? So as a scientist, I would say that this is pretty good prediction. If you do as a physical law, I would be happy, okay? The one on the right is just to show you that we didn't cherry pick one point, and you can do as many points as you want. This works pretty well. What we did here is that particularly we changed the dimension, okay? So this is for the interpolation part. What about the variance part? I don't explain you again the whole story because it's the same. The interpretation of the plot is the same. And I would say that in this case, as a scientist, I would say This is not as perfect as before, still pretty good. I'm still quite happy about this, okay? It's not perfectly overlapping. You see that at the border, you start to diverge a bit, but across a large scale of number of points, it still describes pretty well what's going on. Let me skip this for now. Now we put all the errors together. And again, just look now at this right up plot. This is again the number of points. This is putting the two pieces together, the variance and the interpolation error. The blue is the true, the orange is the bound up to the best fitting constant, okay? And again, I would argue that quantitatively, this is not the best. Qualitatively, it allows to make predictions, okay? For example, one prediction it allows to make is, this is the divergence of the error. When n, if I fix d equal to 5 and now n becomes large, at some point this method is not going to work. What do I expect to happen if I let d become larger? Well, that this point will happen later, right? Because I need more points to occupy my high dimensional space. And this is it. Okay, it still does diverge, but later, because here d is 11 instead of 5. Also, I would argue that oftentimes in practice, you work with problems that are bigger than d, okay, than d equal to 11, and you might or not at 5,000 points. And so you might be in the regime where you see the error going down and not going up, just because you don't have enough data to see it going up. And so you effectively see this method to work, so to say, because you don't see when you start to be bad. What's this plot in the middle? Is the plot where instead of plotting against n, I plot against gamma, okay? So this is again the test error, and this is the blue one is the true one. This flattening on the side is due to the fact that this is a finite dimensional computation trying to mimic an infinite dimensional situation. And what you see here is that again, this bound seems to capture pretty well what's happening in the middle, okay? That there is this trade-off. It's kind of way off at the border. And we know that that's what we expected from the assumption in the math, okay? So I think I'm running late. So let me highlight you a couple of things, okay? One is, okay, this was simulated data. What about real data? Well, what do I expect? What I expect is, give me a data set. If I pick a small scale and a small nu, maybe I don't need to regularize, because the variance effect is going to be cured by the fact that I took a large space, okay? This is large space, this is small space, and here is lambda, okay? I didn't tell you this. Here you see that I don't need lambda, okay? If lambda is big, I ruin. If lambda is small, nothing happens. And that's because the condition number is already been taken care of by choosing a large space. Here, I make the space smaller, and I start to see instability. And now lambda is needed, okay? So it seems that this effect is real. This is classification is even more clear in regression. So let me see. I don't know how to stop this. So and let it go, and I'll do it again. So what I'm going to show you now, if I manage, is a simulation where what you see is the true function, the data, and the minimal norm interpolant that correspond to different scales. Okay. Again, we have a law. Okay, we have an equation. Let's see what it predicts. What it predicts is that if gamma is very large, the variance term should dominate, and it should be something that is very oscillating. You should not see something smooth. That's the new thing, to me at least. Then you make gamma small, you get something nicer. Then you make gamma too small, you're putting spikes on the points, and it sucks again. Okay, at the beginning is large gamma, and the end is small gamma. And again, here I'm going to show you another one, which is kind of the same. The new, you definitely expect the end. I guess the question is that it is for me, as for my statistical background, I was not expecting the beginning. I would have expected the large gamma to always be good. And I've never seen it because I never killed the lambda. I usually put them all together. So this effect was always hidden to me. Okay, this is what I call so let me finish this and then I kill the next one, which is what I call the machine learning Rorschach test. I'm going to show you a movie, okay? And it's the same story. Now it's a bit not as fun, but this theory is at the beginning or at the end, the space is smaller, okay? You have to say when it's smaller. Okay, let me show you again. No, sorry, this next one. Oh, the name is wrong. So it's crazy, and then it settles down, okay? If you show me this plot 2 years ago, would I say, well, clearly at the beginning, I am a huge space, and it overfits, but at the end is great. Then, of course, at this point, you can say, well, let me look closer. Hey, wait, there is a kink here. This space cannot be so small because I managed to put a kink, so it must be big. And you're right, because actually here, the space is the largest space you have. The largest space you have, and what I did is that I moved the smoothness, okay? I choose the smallest smoothness, and that's enough to make the problem stable. So I do not see the effect of the spikes, okay? Because I play with nu and gum in a better way. At the beginning, sorry. At the beginning, the space is large, and I do have the variance killing me, okay? This is where there is no noise. It's not a very fun plot. Nothing happens because basically there's nothing to cure. Okay, I choose the parameter in such a way that interpolation is good, and there is nothing to cure with the noise. So here, the effect of small scales and so on doesn't matter. There's nothing. So the behavior, the crazy behavior, were due to the noise, as expected. Okay, so let me finish here. Okay, what to say? Again, this was a story. It's a story which is part of intuition and part of mathematical results. And this is basically saying that there is a reason why large spaces, this suggested reason why large spaces, so if you want overparameterization, might be useful. And that's because they allow more stable behavior, not with respect to the sampling, but with respect to the noise. Okay. Of course, making this more general and try to build kernels for which you get consistency is a challenge. I think it also suggests that oftentimes that you might be working either in a regime where you don't need regularization, but there will be a regime eventually where you need it, okay? And so I think a little bit of lambda never hurts. And I think I'll stop here. Sorry, I'm a bit long.